So Einstein thought that, well, if I make two postulates, then I can move on. The first postulate was that the laws of nature and the results of any experiment you perform in different frames of reference should give the same results. So, laws of nature and the results of experiments should be the same in any inertial frame of reference. And there's no way to prove this, I guess, but if you think about it, if you're driving a car along the road and then you see something that's, when you look out the window of the car, you see something different happening from the guy who's walking on that street, well, then you would think that you were crazy, right? And that's, if this postulate doesn't hold, you could expect to see results like that. For example, if you hit the pedestrian, he would perhaps survive in his frame of reference, but he would die in yours. It would be completely nuts. And because of this, you would also have that the speed of light would have to be the same in all inertial frames of reference. So let's see, the speed of light is the same in any inertial frame of reference. And this is consistent with the fact that we discussed before, that C is equal to 1 over epsilon naught mu naught under the square root, because now the static experiment relates to the movement of the waves of light, and if I have the same results from a static experiment in one frame of reference and the same result in another frame of reference, well, then the speed of light must be the same as well, because now we're assuming that the Maxwell equations are correct in all frames of reference. And it's also consistent with the Michelson-Morley experiment, where you had the motion of the Earth moving around the Sun. So this seems like two plausible assumptions based on that history and on the Maxwell equations. So if you now make these assumptions, let's try to determine what is the correct principle of relativity. What is the mathematical transformation of our coordinates in one inertial frame of reference to another frame of reference. So consider the following. We have a coordinate system K. Let's see, x3 perhaps. Doesn't matter. And let's see, relative to this coordinate system K, there is a coordinate system K prime, which is moving at a velocity v. So same as before. Like this. So it's moving along the x1 axis in both systems. Now at t equal to 0, we choose our time so that at t equal to 0, the two coordinate systems coincide. So origin of k prime coincide. Furthermore, we assume that at t equal to 0, there's a flash of light emitted from the origin. So flash of light emitted at, let's see, r equal to r prime equal to 0. And because these coordinate systems coincide at t equal to 0, the flash occurs in this in the origin in both coordinate systems. Now, if you consider system K first, the wavefront of this flash of light is described by the following equation, that x0 square minus x1 square plus x2 square plus x3 square is equal to 0. And this is simply the law of Pythagoras, right? The distance out to a point is equal to the time the light has traveled. And x naught is, of course, ct. So x naught, this is a common notation in so-called 4-vector notation, where you consider time to be a dimension like the other ones, except there's this pesky minus sign, which sort of separates it from the spatial dimensions. But for now, you don't have to think about that. Simply set x naught equal to ct, and then you realize that the wavefront is described by this equation. Now, if you look in k prime, you would see the same thing, right? At the origin, a flash of light is emitted, and the wavefront must be governed by the same equation. So x naught prime minus x1 prime square plus x2 prime square plus x3 prime square is equal to 0. And now if you try to insert the Galilean transformation between these two coordinate systems, you will realize that it doesn't work, of course, as we saw before. And as before, x naught prime is equal to ct prime, like that. Okay. And now we need to figure out what is xj prime in terms of xi, let's say. So xi prime in terms of xj. And these mathematical transformations are called the Lorentz transformations. And they read as follows. X naught prime is equal to gamma x naught minus beta x1. x1 prime is equal to gamma x1 minus beta x0. And x2 prime is equal to x2. x3 prime is equal to x3. And I introduced beta and gamma, which are defined as 1 minus beta square to minus 1/2. And beta, that's simply v over c, where v is the velocity of the coordinate system k with respect to k prime. Okay? So now I'm going to go the other way. Rather than to find these, I'm going to insert them and show that they are correct. And if I insert for x naught prime and x1 prime, x2 prime and x3 prime into this equation, I will hope to get to this equation, because then I will see that this transformation conserves the laws of physics in both frames of reference. Okay? So I insert into the wavefront equation. Let's see. And the wavefront equation was simply x naught prime square minus x1 prime square plus x2 prime square plus x3 prime square is equal to 0. And now I insert the transformed coordinates. So I get that x naught prime square, that's equal to gamma square x naught minus beta x1 square. And then I get a minus x1, that's also changed in the new frame of reference, so that's, C should be a minus sign, gamma square x1 minus beta x0 square. And then there are two more terms which are unchanged, x2 square and x3 square. This should all be equal to 0. Now, if I simply perform the multiplication here and here, we see that the cross terms will disappear. So I'll do that and see if we get something simpler. So gamma square x0 square, that's the first term. Then the cross term, 2 gamma square beta x1 x0 plus the second term square. So that's gamma square beta square x1 square. That's this one. I continue with this one equivalently. I get minus gamma square x1 square and plus 2 gamma square x1, no wait, x1 x naught and a beta minus gamma square beta square x naught square. That's a lot of talking to the blackboard, but that's a lot of writing. And finally I have x2 square and x3 square should be equal to 0. Now you notice that this term and this term is the same except the signs are opposite, so I can take those out of the equation. Doesn't change anything. Now if I tidy this up, perhaps here, then I get gamma square 1 1 minus beta square x naught square. That's when I collect all the x naught terms. I also get gamma square 1 minus beta square x1 square. That's when I collect all the x1 terms. Finally, I have minus x2 square minus x3 square should be equal to 0. And now we have to do some sort of trick to figure out if this is correct. So let's have a look at that. Well, if you look at gamma square, 1 minus beta square, this is actually much easier than it looks because this is 1 over 1 minus beta square, like this, to power 2. That's gamma square. And this is 1 minus beta square. So the square takes away the square root, and 1 minus beta square takes out 1 minus beta square. This is equal to 1, meaning that we get finally x naught square minus x1 square minus x2 square minus x3 square is equal to 0. Et voila. The laws of physics are the same in the two frames of reference if you use the Lorentz transformation to relate the two coordinate systems. So this is the correct principle of relativity in electromagnetism. Any questions? No? Now, there's only one question remaining as to this principle of relativity which we found. And that is, well, what about the mechanical laws of motion? Are those unchanged under a Lorentz transformation? And to find out more about that, I'm going to write out the Lorentz transformation in a bit more detail. So let's see. X naught prime. Wait a second. Okay, so Lorentz in mechanics, perhaps. So if I write out transformations in detail, then that's x naught minus v over c x1 over 1 minus v square over c square. This happens when I write out the gamma and beta. And x1 prime is equal to x1 minus v over c x naught 1 minus v square over c square under the square root, like that. Okay, this doesn't look like the Galilean transformation at all at first sight. Now, if I write this instead in terms of time rather than x naught, let's have a look at that. So I get that t prime is equal to t minus b over c squared, because now we divide by c on both sides, x1 and the same square root, 1 minus, let's say, beta square. And finally, x1 prime is the same for now. Okay, still doesn't look like the Galilean transformation rules. So let's make the following assumption. Let's make the assumption that v is much less than c. Because in all contexts, at least up to the point where that Einstein had considered, the velocity of anything that was moving was always very small. I mean, if you're driving a car, or even if you're a comet swooshing through space, then the velocity is always really, really small compared to the speed of light. So if you look at x naught prime, t prime, that's equal to, well, it's t minus v over c squared, and c squared is enormous, right? So this term I can neglect. So it's 1 over 1 minus v squared over c squared. But this is also really small, because if v is much less than c, then v squared over c squared is a really small number. So this is approximately equal to, let's see, should be t here. So t is approximately equal to t prime, as long as we're not moving too fast. Furthermore, if you have a look at x1 prime, that is x1 minus, and then x naught is ct, so the c goes against the c here, and we're left with vt, like that. And this is exactly the Galilean transformations. There you go. So as long as you're not moving too fast, you're not going to see any relativistic effects. And Einstein's conclusion was the following, that the Lorentz transformation leave the laws both of physics and of mechanics unchanged. The Lorentz transformation leave both mechanics and electromagnetism unchanged. And this is a relatively interesting discovery, I'd say. Now finally, let's become even more convinced about this by having a look at the wave equation in k and k prime, and then we can see if the wave equation doesn't change form, because then we know that the laws of electromagnetism is Lorentz invariant, truly. So first of all, let's write down the wave equation in k. K prime. And notice that I can write it as follows: d dx naught prime square minus d dx1 prime square applied to E is equal to 0. Now we just consider a wave propagating along x1 just to prove the point. This is sufficient. So it's the same as we did in the previous lecture with the Galilean transform. So E is plane wave traveling along x1. And the coordinate systems have the same direction, so x1 hat is equal to x1 prime hat, right? Like this. Like that, and some velocity connecting them. So, all right. As before, we need the differential operators in the two frames of reference. So, as before, we see that d dx naught prime is equal to, by the chain rule, dx naught over dx naught prime d dx naught plus dx1 dx naught d dx1, and the same for d dx1. You perform the same chain rule trick and recall that x naught is equal to gamma x naught prime minus beta x1 prime, and x1 is equal to gamma x1 prime minus beta x naught prime, like that. Okay, now notice the following. This is a linear transformation because x naught is the power 1, x1 is the power 1, x1 and x naught here as well, the power 1. If you had x1 to x1 square, for example, it would be a non-linear transform, but this is a linear transform. So all we need to connect one coordinate system to the other is, of course, as before, dxi prime dxj. As you recall from the tensor part of the course, you see it here, right? So let's determine what these partial derivatives are. So dx naught over dx naught prime. Well, that is simply 1 times gamma. You also have dx naught by dx1 prime. And you see there's also an x1 term here. So that's minus gamma beta dx1 by dx naught prime is equal to minus gamma beta, and finally dx1 by dx1 prime is equal to gamma. So these partial derivatives is all we need to relate one coordinate system to the other. All right, now I can write out dx naught using this equation here. Let's see, dx naught prime is equal to gamma dx naught in the unprimed coordinate system and minus gamma beta dx1, like that. Same procedure as last time for x1 prime, dx1 prime is equal to the following: gamma dx1 minus gamma beta dx naught. So you notice the symmetry, it's basically the same thing, exchanging 1 and 0. Okay, and we're going to need the square of these because that's what shows up in the wave equation. So first of all, let's square the top one. Let's see. So dx naught prime square. And then I simply square this whole right-hand side. So where am I? Down here. So I have a gamma square dx naught square minus 2 beta dx naught dx1 plus beta square dx1 square. And in the same fashion, I calculate ddx1 prime square So d dx1 prime square, well, that's a mouthful, is gamma square d dx1 square minus 2 beta d dx naught d dx1 plus beta square d dx naught square, like that. Okay, and now I just need to add this one to this one, because that's what shows up in the wave equation. So d dx naught prime square minus d dx1 prime square. So I don't want to write up all this stuff again. So I carefully look at the expressions and see that, well, this term and this term is the same, but this minus sign means that they will cancel. So I will just do like this, cross them out, and it simplifies somewhat. Now if I gather the x naught terms first, I get gamma square 1 minus beta square. Looking good, right? D dx naught square. And the other term, that has to do with, let's see, d dx1. So that's also gamma square 1 minus beta square d dx1 square. Because you see I have 1 and minus beta square. Okay, now we recall from the example where you had this flash of light traveling outwards in space, that gamma square 1 minus beta square, that's equal to 1. Meaning that I can just forget about the whole thing. And there you go. The wave operator is now d dx naught square minus d dx1 square. So the wave equation looks the same in the primed and the unprimed coordinate system, because the wave equation is simply d naught square minus d1 square of E is equal to 0. It doesn't change under the Lorentz transformation. Meaning that we finally track down some interesting observations. We have that the laws of physics are the same in all inertial frames of reference. The speed of light is the same in any inertial frame of reference. And this applies both to electromagnetism and to mechanical laws. So this is the beginning of the theory that Einstein used to, well, this is the fundament of Einstein's whole special theory of relativity. His first paper was actually called something like Zur Elektrodynamik der bewegter Körper, or on the electrodynamics of moving bodies. So he didn't, like in some examples you'll see in textbooks, look at trains moving along, emitting light and so on. He looked at the equations of electromagnetism, and this made him find that E is equal to mc square and all those other famous equations. Any questions?
Var det Einstein eller Lorentz som satte opp uttrykket for Lorentz contraction?
Okay, so the question is, was it Einstein or Lorentz who first set up the Lorentz contraction or Lorentz transformation formulas? And the answer is Lorentz, because he said as follows. Well, if this experimental setup, which basically looked like this, there's some light source, beam splitter, some mirrors, like that. He said that, well, if these arms are Lorentz contracted, as it's later been known as, in this direction here, if that is the motion of the ether, so if I say v ether, he found that the experimental results would be reproduced if there was a length contraction of a physical body that was moving into the ether. Okay, so if you have a velocity with respect to the ether, then you would contract by this factor 1 over 1 minus v square over c square. by this factor. And that would sort of rescue the observation if that happened. So this was the origin of the Lorentz contraction. So it has nothing to do with Einstein's version of the theory, really. It's just sort of an ad hoc hypothesis to correct for the observation. So he found the equation, but he didn't quite get it right. Also, he didn't include the time dilation change, which you've heard about, right? Yeah. Anything else? No? Okay, then we'll start on something a bit more down to earth, which is the reflection if you have a thin film on a substrate. Okay. So, wave propagation in layered structures. This is intended both to be a repetition of what we already learned for wave propagation and boundary conditions, but also to give an example of an application of this theory which will let you analyze what happens in these structures. So to recap a bit, we studied the following system where you had x1 was like this, x3 going up, and there's an incoming wave with a vector k, the wave vector of the incoming light. There's a transmitted wave going in direction p, and a reflected wave going in direction q. And there are two materials here. There's one material with index 0 and one material with index 1. And in this medium we have n naught is equal to epsilon r naught. This is the relative dielectric constant in medium 0, and n1 is equal to epsilon r1. I neglect the mu for now because most optical materials are very weakly magnetic, meaning that mu r is really close to 1, so we just neglect that. But it's easy to include in principle. You just put a mu here and here. Okay, I decomposed k as follows. So this is k, and k1. By the way, this is repetition, so if you don't remember or don't understand what I'm going through, then you should ask something, because this is the last opportunity to get this cleared up. Finally, alpha of k 1 omega is equal to k3. So I explicitly incorporate the dispersion relation into this alpha, and the alpha looks like, let's see, k1 omega is equal to epsilon naught of omega. By the way, this is the relative refractive index of medium 0, not epsilon 0. Sorry, the confusing notation. By the way, I can use, let's see, I can use n0 of omega squared perhaps. Omega squared over c squared minus k1 squared. Because as we recall, k1 squared plus k3 squared has to be equal to omega over c squared. Right? That's the dispersion relation. And here I incorporate that explicitly into alpha, which makes sure that I'm always on this line in the dispersion diagram where k squared is equal to omega squared over c squared. Now I write the electric field in medium 0, where I for the moment consider the Senkrecht polarization, and I divide by some constant electric field, so I don't have to incorporate it into these expressions. It's equal to e to I k1 x1 minus I alpha 0 of k1 omega x3, where the 0 signifies that I'm in medium 0, meaning that I insert n0 here. Okay. So that's the incoming light. There's also a reflected wave, Rs of Q1, K1. So this is the reflection amplitude. If I have light incoming with a K parallel, I get light outgoing with this Q parallel with the amplitude Rs. Okay? And e to I Q1 x1 plus I alpha naught, because I'm in medium 0, of Q1 omega x3. And this is all harmonically time dependent. But to save myself some writing, since everything has the same factor e to minus I omega t, I'm going to drop that from now on. But it's always there. Just that it will be the same on each side of the equation symbol always, so I can just take that away. So electric field in medium 1, Senkrecht polarization, 1 over EC is equal to Ts of P1 K1 e to I P1 x1 minus I alpha 1 of P1 omega x3. That's a lot of writing. This is what we started out with for the electric field when we have a Senkrecht polarization. Does everyone remember what Senkrecht polarization means? Well, someone has to remember it. Hmm? Yeah, the polarization is orthogonal to this x1, x3 plane. And the polarization is always defined by the electric field. So the electric field is like this. It's going in and out of the plane. It's oscillating, of course. I can't say if it's in or out, but it's in or out of the plane. If you have parallel polarization, then the E field is somewhere in the plane. But then I can work with the magnetic field in the same way. For example, H or B, if I prefer. And then it will look exactly the same, so I won't go through parallel polarization because it's the same math. Let's see. And we recall that we found Rs and Ts by matching the boundary conditions. So boundary conditions gave us, first of all, that K1 is equal to Q1 is equal to P1. The transverse wave number is conserved, or the lateral wave number if you want. And we found expressions for the reflection amplitude, Rs, and the transmission amplitude, Ts. Now, because K1 is equal to Q1 and P1 is equal to K1, then I can sort of neglect this dependence. So this is something I inserted to be general in the beginning, but as we found out that Q1 is equal to K1, always, then I can just neglect that. This leads to the Snell's law of refraction and the law of reflection saying that the incoming angle is the same as the outgoing. So, a new way to find the same old physics you know from before. So that's the recap. Now what are we going to discuss in this lecture and the next? Well, that is the following geometry. So I have a surface here and k vector, incoming wave of light, plane wave. And this is a thin film of thickness d. So I have, let's say, air, and then some film, and then I have, let's say, glass. A typical example is if you have glasses, then your glasses typically have some sort of anti-reflection coating. So you have a thick piece of glass which does sort of the geometric optics of bending the light rays that come into your eye. And there's a film to take away the reflections that are very annoying. So if you have, for example, cheap sunglasses, you'll see annoying reflections from the inside of the glass. Okay, so typically, well, this is a typical setup. It's not necessary. We could have water and we could have plastic or whatever, but doesn't really matter. So n in region 0, that is equal to 1 if you have air. In medium 1 here, then you have n1, which is greater than n0. And here you have n2 is greater than n0 too. Okay? Now, if you consider this geometry, you'll notice that, well, you could have transmission, like this perhaps, but you could also have reflection. That's fine, but what if you have transmission here and reflection there? Then you get a wave traveling upwards, and then this wave will also have reflection and transmission. So you get all these bouncing waves inside the film, which you will have to take care of when you're going to match the boundary conditions. It's not simply a wave going down, a wave going up. Like here, you have a wave going up because of the plus, and a wave going down, like that. But you have to sum up all the waves going up and down inside the film and try to figure out the sum of the outgoing waves in the upper area and the sum of the transmitted waves. Because you're not interested as such in what happens inside the film, but rather, if I shine light on the film, on the substrate, what comes up and what goes down. Okay, so I hope the geometry is clear now. And we want to discuss two cases. The first is if you have a real angle here, right? If this angle phi 0, say, if that is a real angle, then you have light coming in here and being reflected and transmitted. So that's the sort of reflection part of it. Afterwards, I hope to have time to discuss if you have light traveling inside. So if k is on this side, shine light on from here, let's say, and assuming that this index of refraction is larger, then you get guided waves. So topic 1, reflection and transmission. Topic 2, guided waves. And we're going to start out with reflection and transmission. And I put a compendium on the web page, which is written by Ola Hunderi. And this sums up the theory I'm going to go through, the first part of that compendium. Okay, so okay, I'll try to get to the first reflection coefficient. So, if we keep working with a senkrecht polarized light without me having to put S's everywhere, then we can write that E in medium 0, senkrecht polarized, is equal to E to I K1 R1. So I changed notation a bit. This is the wave vector in medium, oh sorry, that's 0, right? So I'm somewhere in medium 0. This is the incoming wave, it's going down. And then there should be plus R01 E to I Q1 R1. So K0 is the wave vector here of the incoming light, and R01, that's the Fresnel coefficient, which we found before from the boundary conditions of when we have an incoming wave here, how much is reflected out again. So going from medium 0 into medium 1, what is the reflected amplitude? That's R01. Okay, so this is the incoming wave. This is the first reflected. And then there are more terms which we don't know what are, right? Higher order reflections. And that comes from when you have this layered structure, you have some wave going down and up like this. That's the first of those terms. And then the next term is another reflection. So it should be a hopefully converging series of reflections going down, up, like that. Now, if you consider this first bounce first, then we'll see easily what the higher order terms are. So in medium 0, I have some incoming angle phi 0. And then I have in medium 1 a different phi because of the Snell's law. And there was this first reflection, that one. And this will give us the second reflection. Okay, so this phi 1 will also appear here. Now there's going to be an interference effect here if this length is smaller than the coherence length of the light. So if this is, let's say, a few microns, then we can expect some sort of interference phenomenon. And what we need to know now is the phase difference from this wave to this wave, because as you can see, this wave travels this distance L1, L0 when interfering with the wave traveling to L1. Okay? So the wave fronts here have different path lengths, meaning that we get a phase difference which is K1 times 2 times L1, where L1 is this length here, minus K naught L naught. And K1, that is simply 2 pi over lambda 1, or 2 pi over lambda naught, which is the vacuum wavelength, times N1. Okay, so the index of refraction comes in there. Now I define delta as 2 pi over lambda naught N1. So this is K1 times d cosine of phi naught. And you can actually show that in this geometry the phase difference factor is going to be simply e to 2I delta. Okay, so this is simply a bunch of trigonometry because you have to figure out how far is this and how far is this as a function of the incoming angle. You have to use the Snell's law of reflection and some stuff like that, but this is what you end up with, and you're all capable of it. So if you want to see where this comes from, you just sit down, you draw the triangles very carefully. This is a right triangle, You can use sines and cosines to relate these to each other. And in the end, this is what you end up with. And now we see that the E field becomes the following. So I continue for a few more minutes, and then we get to the reflection coefficient, and then we take a break until Wednesday, okay? So E naught is equal to E to I K1 R1, which is the incoming, and then R01 E to I Q1 R1. Sorry, this is 0. I messed with the indices of the media. So that's the first reflection from the top interface between medium 0 and 1. And then there's the first bounce wave, which is T 0, 1, R, 1, 2, T, 1, 0, E to I, Q, 0, R, 0. As we recall, the parallel wave number was conserved. And E to I, 2I delta. So there's a phase difference here on this exponential, which came from the difference in path length. And then there is the next reflection. But the next reflection is easy. Now, what is this? If you look at this first bounce, you have transmission here. So that's T01. Then I get a reflection on the interface 1 to 2. So I'm coming from medium 1 and trying to get into medium 2, but I'm reflected. So you have finally have some transmission here, which is T10. So coming from medium 1, I'm transmitted into medium 0. And the next bounce now is the same thing. You simply add this phase factor and R10, R12, T10. Okay? Meaning that this is a geometric series. Because I can write it as follows. Let's see. The total reflection coefficient is R01, which is the old one from just the top layer, plus T101, R12, T10, E to 2I delta, then sum n from 0 to infinity, and then E to 2I delta to power n, because for each bounce you get this extra phase. And finally R12, R01 to power n, because for each extra bounce I get an extra reflection up here and down here. Okay? And this is a geometric series, so it's actually easier to just include infinitely many reflections, giving me that the total reflection amplitude is R01, which is what you had for just a simple interface, and then plus T01, R12, T10, E to 2I delta, over 1 minus E to 2I delta, R12, R01. That's the total reflection amplitude when you have this thin film on top of a glass substrate. And we'll finish it up on Wednesday. Any quick questions? Okay, see you Wednesday.